Schweinfurt, Germany, October 14, 1943, 11:47 hours, and Hauptmann Ernst Vogel, commanding the 4th Heavy Flak Battalion defending the ball-bearing factories that supply 60% of Germany's critical war production, watches through his rangefinder as American B-17 bombers approach at 25,000 feet in tight combat box formations, confident that his battery of 16 88mm guns with radar-directed fire control can destroy any bomber receiving a direct hit from shells designed to tear aircraft apart with explosive force and shrapnel fragments. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. His crews have shot down 47 Allied bombers over the past 8 months using techniques perfected through 2 years of air defense operations, and Hauptmann Vogel knows from extensive experience that a single 88mm shell detonating within 20 meters of a bomber typically causes catastrophic structural failure, while direct hits invariably result in immediate disintegration or uncontrollable fire. What Hauptmann Vogel cannot possibly know, what no German flak commander could comprehend despite their technical expertise and combat experience, is that Boeing engineers in Seattle have created an aircraft with structural redundancy so extensive, fuel systems so protected, and damage tolerance so exceptional that B-17s will absorb direct hits from 88mm shells that blow meter-wide holes in wings and fuselage, lose entire sections of tail surfaces, fly with 2 or 3 engines destroyed, and still carry their crews 400 miles back to England. And within 3 hours, Vogel will watch in disbelief as bombers his crews hit directly, aircraft that should be falling in flames, maintain formation and continue their mission despite damage that would destroy any other aircraft in existence. The confidence of German flak batteries defending the Reich comes from systematic development of anti-aircraft weapons and tactics that have evolved since the Spanish Civil War, from the integration of radar fire control that allows accurate engagement of high-altitude targets, and from the deadly effectiveness of the 88mm Flak 36-37 gun that is proven capable of destroying any Allied bomber when shells detonate close enough to inflict damage. Oberlieutenant Friedrich Kaufmann, fire control officer for Vogel's battery, has calculated thousands of firing solutions using the sophisticated Wurzburg radar system that tracks incoming bombers and provides continuous range, altitude, and bearing data to the predictor mechanism that aims the guns. The system represents the pinnacle of German electromechanical engineering, radar detection at ranges exceeding 40 kilometers, tracking accuracy sufficient to predict bomber positions seconds into the future, and automatic transmission of firing data to gun crews who need only load and fire on command. The 88mm Flak 36 gun that forms the backbone of German air defense represents one of World War II's most versatile and deadly weapons, equally effective against aircraft at high altitude and armored vehicles on the ground. The gun fires a 20-pound high-explosive shell to altitudes exceeding 30,000 feet, with time fuses set before firing to detonate at calculated heights near target aircraft. Wachtmeister Franz Dieter, gun commander for gun number 3 in Vogel's battery, understands his weapon's capabilities intimately after 18 months of continuous operations. Muzzle velocity of 2,690 feet per second, giving the shell enough kinetic energy to reach stratospheric altitudes, fragmentation pattern that spreads over 100 feet when the shell detonates, and the psychological effect of sustained barrage fire that forces bomber formations to fly through curtains of explosive-filled airspace where avoiding all fragments becomes mathematically impossible. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. German flak doctrine emphasizes concentrated fire from multiple batteries to create boxes of exploding shells that bomber formations must traverse, accepting that individual shells rarely score direct hits, but that sustained barrage fire inevitably causes casualties through accumulated near misses and the occasional lucky hit. Hauptmann Vogel has positioned his 16 guns to create overlapping fire zones covering the approaches to Schweinfurt's industrial district, coordinating with adjacent batteries to ensure no altitude or bearing allows bombers to avoid flat coverage. The doctrine has proven effective throughout 1943, with 8th Air Force bomber losses averaging 5 to 7% per mission, rates the Americans can sustain only through massive aircraft production and crew training pipelines that German planners believe will eventually prove unsustainable. The B-17 Flying Fortress approaching Schweinfurt on October 14, 1943, represents the culmination of Boeing's pre-war vision of a strategic bomber capable of defending itself, delivering substantial bomb loads, and surviving in hostile airspace through sheer structural integrity and defensive firepower. The aircraft's designation, Flying Fortress, initially seemed like marketing hyperbole when Boeing coined the term in 1935, but combat experience has validated the name as pilots return in aircraft so badly damaged that ground crews wonder how they remained airborne. Technical Sergeant Robert Anderson, crew chief for the 379th Bomb Group, has witnessed B-17s land with holes larger than walk-through, with control surfaces partially destroyed, with engines torn from their mounts, damage that would doom any other aircraft but which Flying Fortresses somehow survive. The engineering philosophy underlying the B-17's exceptional survivability begins with structural redundancy that allows the aircraft to maintain flight even when primary load-bearing members are damaged or destroyed. Boeing's design team, led by Chief Engineer Edward Curtis Wells, incorporated multiple load paths throughout the airframe, ensuring that if one structural member fails, adjacent members can carry the load temporarily. The wing structure includes multiple spars running from root to tip, with the rear spar capable of supporting flight loads if the main spar is damaged. The fuselage employs stressed skin construction, where the skin itself carries substantial structural loads, allowing the aircraft to maintain integrity even when internal frames are damaged. Control cables for rudder, elevators, and ailerons are routed through multiple pathways, providing redundancy if flaks sever primary cables.
The fuel system represents perhaps the B-17's most critical survivability feature, incorporating self-sealing tanks that automatically close punctures and prevent catastrophic fuel loss or fire. The self-sealing technology, developed by United States Rubber Company, uses multiple layers of rubber and fabric that swell when exposed to fuel, creating plugs that seal holes up to approximately 1 inch in diameter. Captain James Mueller, engineering officer for the 91st Bomb Group, explains the system's operation. When a flak fragment or machine gun bullet penetrates a fuel tank, gasoline contacts the self-sealing layers which immediately begin absorbing fuel and expanding. Within seconds, the expanding rubber creates a seal that stops fuel loss. The tank might lose 50–100 gallons before sealing completes, but that's far better than losing the entire 1,700-gallon capacity, or worse, having fuel spray ignite from hot fragments. The 4 Wright R-1820 Cyclone engines powering the B-17 provide not just propulsion but critical redundancy that allows the aircraft to maintain flight even with multiple engines damaged or destroyed. Each engine produces 1,200 horsepower at takeoff, and while all 4 are required for maximum performance and altitude, the B-17 can maintain level flight at reduced altitude on 3 engines, and exceptional pilots have returned to base on 2 engines by sacrificing altitude gradually throughout the return flight. Lieutenant Colonel Robert Morgan, pilot of the famous B-17F Memphis Belle, describes flying on 3 engines as challenging but manageable. You lose altitude capability and speed, but the aircraft remains controllable and can get you home if you're willing to accept landing at the first available field, rather than making it all the way to your home base. The defensive armament of the B-17, evolving from early models with limited guns to later variants bristling with 1350 caliber machine guns, serves dual purposes: actual destruction of attacking fighters and psychological deterrence that makes German pilots more cautious. The guns are positioned to provide overlapping fields of fire covering all approach angles, though blind spots inevitably exist that German fighter pilots learn to exploit. Staff Sergeant Michael Romano, ball turret gunner with the 306th Bomb Group, understands that his twin 50 calibers serve primarily to make attacking fighters' approach more difficult. We rarely shoot down fighters. They're too fast, and our aim from a vibrating bomber at 25,000 feet isn't accurate enough. But we make them dodge, disrupt their approach, and force them to worry about our fire while setting up their attacks. That split attention sometimes causes them to miss or break off. The crew positions within the B-17 reflect design philosophy, balancing operational requirements with survivability considerations. The pilots sit side by side in the cockpit, with armor plate behind their seats, protecting against rear attacks, but leaving them exposed to frontal assaults. The bombardier occupies the nose compartment during the bomb run, an extremely vulnerable position offering unobstructed view for precise bombing, but minimal protection. The navigator works at his table in the nose section, maintaining position plots and calculating courses. The radio operator, flight engineer, and waist gunners occupy the mid-fuselage section. The tail gunner sits in the most isolated position, separated from other crew members by the length of the fuselage, often the last to escape if the aircraft is fatally damaged. What makes October 14, 1943 significant in the history of strategic bombing is not the target. Schweinfurt has been attacked before, but the scale of forces involved and the determination of both sides to achieve decisive results. The 8th Air Force commits 291 B-17s to the mission, the largest force yet assembled for a single target, betting that concentrated attack can destroy enough of Schweinfurt's ball-bearing production to cripple German armament manufacturing. German defenses, aware of Schweinfurt's strategic importance, commit their strongest fighter forces and heaviest flak concentrations to defending the factories. The resulting battle will prove one of World War II's costliest air engagements, with 60 B-17 shot down and another 17 damaged beyond repair. But it will also demonstrate the Flying Fortress's remarkable ability to absorb punishment and return home. Hauptmann Vogel's battery begins tracking the approaching bomber formations at 11:42 hours when Würzburg radar detects the lead groups at 43 kilometers range. The radar operators provide continuous updates as the bombers close: altitude 7,600 meters, speed 290 kilometers per hour, bearing 247 degrees. The predictor mechanism calculates firing solutions accounting for altitude, speed, wind, and the time required for shells to reach detonation altitude. Gun crews load shells, set time fuses according to transmitted data, and await firing commands. At 11:47 hours, with bombers at 18 kilometers and clearly visible as dark shapes against high clouds, Vogel gives the order to commence firing. The first salvo of 16 88mm shells leaves Vogel's guns with distinctive cracks that echo across the Schweinfurt industrial district. The shells climbing toward the bomber formations at 820 meters per second. The time fuses, set to detonate at 7,400 meters altitude, function precisely as designed, creating a pattern of black smoke bursts among the lead bomber group. Through his binoculars, Vogel watches the familiar pattern. Black puffs appearing among the bomber formation as shells explode, some bursts close enough to bombers that fragments must be striking aluminum skin, others farther away but contributing to the barrage that forces bombers to fly through increasingly dense explosive fields. Second Lieutenant William Lawley, pilot of B-17F serial number 42324, nicknamed Cabin in the Sky 2, experiences his first indication of flak at 11:47 hours and 23 seconds when a black burst appears 50 yards ahead and slightly above his position in the formation. The explosion creates a pattern of smoke that dissipates quickly in the thin atmosphere at 25,000 feet. But Lawley knows that the smoke marks the location of thousands of steel fragments radiating outward at velocities exceeding 3,000 feet per second. The fragments, ranging from marble-sized chunks of shell casing to tiny shards of explosive shattered metal, carry sufficient kinetic energy to penetrate aluminum skin and damage or destroy anything they strike: engines, control surfaces, fuel tanks, or human bodies.
The flak barrage intensifies as additional German batteries join the engagement, creating a three-dimensional matrix of explosions that the bomber formations must traverse to reach their target. Lawley counts over 40 burst patterns visible simultaneously, and he knows that represents only a fraction of the shells being fired. Many explode out of visual range, and others fail to detonate properly. The psychological impact of flying through sustained flak fire challenges even experienced crews, as each burst might contain the fragment with your name on it, and there's nothing to do but maintain formation, hold steady, and trust that mathematical probability favors survival despite the apparent density of explosive fire. At 11:59 hours, Hauptmann Vogel's gun number 5 achieves what should be a kill, a direct hit on a B-17 in the second combat box, the shell detonating less than 5 meters from the bomber's left wing root. Through his binoculars, Vogel clearly sees the flash of detonation, sees debris flying from the impact point, sees the bomber shudder from the explosive force. Standard experience says this bomber should begin falling in flames or break apart from structural failure within seconds.
Instead, the B-17 maintains position in formation, its pilots apparently retaining full control despite damage that Vogel knows must be catastrophic. Captain Richard Fisher, piloting the B-17F that just absorbed the direct hit, experiences three simultaneous emergencies as fragments from the 88mm shell tear through his aircraft. The number 2 engine erupts in flames as fragments sever fuel lines and ignite leaking gasoline. Multiple hydraulic lines rupture and spray fluid throughout the bomb bay, and shrapnel penetrates the cockpit area, causing injuries to himself and his co-pilot. The impact sounds like someone struck the aircraft with a giant hammer, a metallic crash that reverberates through the airframe, followed by the immediate howl of wind through holes torn in the fuselage skin. Fisher's training takes over as he fights to maintain control despite pain from fragment wounds in his left shoulder and the shocking realization that his aircraft has just been hit hard enough to potentially kill it. The self-sealing fuel tanks demonstrate their value within seconds of the hit as punctures seal automatically, preventing fuel loss that would quickly drain the tanks feeding the damaged engine. The fire suppression system, activated by Fisher's co-pilot Lieutenant James Brennan despite his own injuries, floods the number 2 engine nacelle with CO2 that starves the fire of oxygen. Within 30 seconds, the flames extinguish, leaving a blackened, non-functional engine, but preventing the uncontrollable fire that typically dooms damaged bombers. The aircraft, designed to fly on 3 engines, compensates for the lost power as Fisher adds throttle to the remaining engines and maintains formation position through sheer determination and superior piloting skill. Hauptmann Vogel, watching the bomber he knows his battery hit directly, experiences cognitive dissonance as the aircraft continues flying in formation despite damage that should have destroyed it. He orders his crews to maintain fire, to keep pouring shells into the bomber stream, but part of his mind struggles to reconcile observation with experience. Hundreds of bombers destroyed throughout his career fell quickly once hit hard enough to cause visible damage. Fuel fires that consumed aircraft in seconds, structural failures that broke bombers apart, control damage that sent aircraft into unrecoverable dives. This bomber absorbed a direct hit that should have created any of those failure modes, yet it flies on, apparently damaged but controllable. The bombing run continues as surviving B-17s approach their release points over Schweinfurt's ball bearing factories, bombardiers peering through Norden bomb sites to align crosshairs with assigned targets. The flak intensifies as bombers slow slightly and fly straight and level during the critical seconds when bombs must be released with precision, creating opportunities for German gunners who can now predict bomber positions with greater accuracy. Lieutenant David Martinez, bombardier in Cabin in the Sky 2, focuses on his bomb site despite the chaos around him, blocking out the sound of flak explosions and the knowledge that his aircraft has already been damaged, concentrating solely on the mathematical problem of calculating the exact instant when his bombs must be released to impact the assigned target. At 11:53 hours, 229 B-17s released their bomb loads over Schweinfurt, approximately 1,500 tons of high-explosive and incendiary bombs that fall toward the factories below. The psychological relief of bombs away proved temporary, as the formations must now survive the return flight through the same gauntlet of flak and fighters they traversed inbound. Many damaged bombers that maintained formation through sheer crew determination during the bomb run now begin falling behind, their reduced speed and altitude making them priority targets for German fighters waiting to pick off stragglers. Captain Fisher's B-17F, having survived the direct flak hit and completed its bomb run, now faces the challenge of returning to England with one engine destroyed, hydraulic systems compromised, and multiple crew injuries requiring medical attention. Fisher calculates his options. The aircraft can maintain altitude on 3 engines, but uses fuel faster than designed, meaning range becomes questionable. Hydraulics loss means landing gear may not extend properly and brakes might not function, making landing hazardous. Crew injuries need treatment sooner than later. Despite these challenges, Fisher decides to attempt the full return to their home base at Bassingbourn rather than diverting to closer emergency fields, trusting his aircraft's ability to keep flying despite catastrophic damage. The formation exercises German airspace, running a gauntlet of fighter attacks and continued flak fire from batteries along the route. German pilots conserving ammunition for maximum effect, focus on damaged bombers struggling to maintain formation or falling behind. The B-17's defensive armament proves critical during these attacks, as waist gunners, ball turret gunners, and tail gunners engage attacking Me-109s and FW-190s, attempting to finish off wounded bombers. The combat degenerates into running battles, where individual bombers fight for survival, their gunners desperately trying to keep fighters at distance, while pilots maneuver to maintain position with friendly aircraft.
Vogel's battery continues engaging bombers throughout their egress, firing until the last aircraft pass beyond effective range. His crews have expended over 800 rounds of 88mm ammunition, achieving multiple hits that should have resulted in significant bomber losses. Yet watching through binoculars, Vogel counts only 3 confirmed kills from his battery's fire, aircraft that exploded or fell in uncontrollable dives. Many more bombers show visible damage, trailing smoke or flying with obvious control difficulties, but they remain airborne and appear to be maintaining course toward England. The ratio of hits to kills proves far lower than his experience suggests should occur. The flight across the English Channel represents critical moments for damaged bombers, as ditching in the cold water means probable death for crews even if they survive the crash. Fisher's aircraft, having flown nearly 400 miles on 3 engines with extensive battle damage, faces one final challenge: landing at Bassingbourn with questionable hydraulics and the knowledge that his aircraft has sustained structural damage that might cause failure during landing stress. Fisher briefs his crew on emergency procedures, ensures everyone has assumed crash positions, and begins his approach with emergency equipment standing by on the runway.
The landing proves anticlimactic after the drama of combat and the long flight home. The hydraulics, though damaged, provide sufficient pressure to extend landing gear and activate brakes. The structural damage, while extensive, does not compromise the airframe's integrity during landing loads. Fisher brings his aircraft to a safe stop on the runway, and as he shuts down the 3 surviving engines, the reality hits him. They made it home in an aircraft that absorbed a direct hit from an 88mm flak shell, the kind of damage that should have destroyed the bomber and killed its crew. Ground crews examining Fisher's B-17F after the mission document damage that exceeds anything they've previously seen on an aircraft that successfully returned to base. The left wing shows a hole approximately 4 feet in diameter where the flak shell detonated, destroying internal structure and creating a gaping wound that exposes wing spars and fuel tanks. The No. 2 engine is a total loss, its internal components shredded by fragments and its cowling burned from the brief fire. Fragments penetrated the cockpit area in dozens of locations, miraculously missing critical flight controls, but causing the injuries to Fisher and his co-pilot. The fuselage shows over 200 separate fragment holes, some small enough to insert a finger, others large enough to fit a fist. By any reasonable assessment, this aircraft should not have made it home. Technical Sergeant Anderson, inspecting the damage, recognizes immediately that he's witnessing validation of Boeing's design philosophy. The wing, despite catastrophic local damage, maintained structural integrity because the rear spar carried loads when the main spar was damaged. The fuel system prevented fire because self-sealing tanks closed punctures automatically. The engines provided redundancy, allowing flight to continue on 3 power plants. The structural design distributed loads so that localized damage did not propagate into catastrophic failure. Every redundancy, every safety factor, every engineering decision that added weight and complexity to the design proved its value by bringing this crew home alive. The broader mission statistics from the October 14th Schweinfurt raid tell a story of devastating losses. 60 B-17 shot down, 5 more crashed in England, 12 damaged beyond repair, and 121 damaged but repairable, but also of remarkable survival. Of 291 bombers dispatched, 171 returned to base having absorbed various levels of damage. Many of those returning bombers sustained hits that German gunners and pilots believed were kills, damage that should have destroyed any aircraft, yet the B-17s kept flying, brought their crews home and could be repaired to fly again. The psychological impact on German defenders watching bombers they hit survive and continue their missions proved as significant as any tactical result. Hauptmann Vogel, filing his after-action report, struggles to explain the discrepancy between observed hits and confirmed kills. His battery achieved multiple direct hits or very close near misses, yet only 3 bombers fell in his sector. He writes, "American bombers demonstrate survivability far exceeding previous aircraft encountered. Direct hits causing visible major damage frequently fail to bring aircraft down. Structural integrity and continued flight despite catastrophic damage suggests engineering design specifically optimized for survival in heavy defensive fire. Recommend increased shell velocity and explosive content if possible to overcome apparent damage tolerance." The intelligence analysis of returning B-17s from the October 14th Schweinfurt raid begins within hours of the last bomber's landing as engineering teams document damage patterns that reveal both the effectiveness of German defenses and the exceptional survivability of Boeing's design. Major Thomas Whitfield, Chief Engineering Officer for 8th Bomber Command, coordinates examination of 171 damaged bombers that returned to English bases, cataloging over 8,000 separate instances of battle damage ranging from single small-caliber bullet holes to catastrophic structural damage that should have caused aircraft loss. His preliminary report, completed October 16th, concludes that B-17 survivability exceeds all previous estimates, with aircraft returning despite damage that would destroy any other bomber type currently in service. The systematic documentation of battle damage provides empirical validation of engineering decisions made years before combat testing. Boeing engineers examining photographs and damage reports recognize design features functioning exactly as intended: redundant wing spars carrying loads when primary structure fails, self-sealing tanks preventing fires and catastrophic fuel loss, engine firewalls containing blazes that would otherwise spread to fuel systems, compartmentalized fuselage design preventing fragment damage in one section from compromising entire aircraft. Captain Fisher's B-17F, with its meter-wide wing hole and 200-plus fragment penetrations, becomes a case study in damage tolerance as engineers calculate that the aircraft flew home with approximately 35% of its design structural capacity compromised.
German technical intelligence, analyzing wreckage from the 60 B-17s that failed to return, struggles to understand why these particular aircraft were destroyed, while others with apparently similar damage survived. Ober-engineer Carl Schmidt, examining wreckage of a B-17 that exploded after a direct flak hit, notes in his report, "Catastrophic failure appears to result from fragment penetration of bomb bay, while aircraft still carried armed ordnance, causing sympathetic detonation of bombs that destroys aircraft instantly. Similar damage to aircraft that had already released bombs might prove survivable. American bomber design demonstrates sophisticated damage tolerance, though vulnerability to hits in critical areas remains exploitable." The evolution of B-17 design through successive models reflects lessons learned from combat operations and systematic incorporation of survivability improvements. The B-17E, introduced in 1941, added tail guns to defend against rear attacks and increased armor protection for crew positions. The B-17F, operational throughout 1943, incorporated self-sealing fuel tanks, improved oxygen systems for high-altitude operations, and strengthened landing gear to accommodate higher gross weights. The B-17G, entering service in late 1943, adds a chin turret with twin .50 caliber guns to defend against frontal attacks that German fighters increasingly employ. Each modification adds weight and complexity, but improves crew survival probability, a trade-off that commanders accept because returning experienced crews proves more valuable than marginal performance improvements. Lieutenant Colonel Robert Morgan,
completing his 25-mission combat tour in Memphis Belle and transitioning to training command, becomes one of the B-17's most vocal advocates based on personal experience with the aircraft's damage tolerance. During his tour, Memphis Belle sustained battle damage on nearly every mission, including 2 instances of direct flak hits that destroyed significant portions of the aircraft's structure. Morgan's detailed accounts of these missions provide insights into how crews react to catastrophic damage and continue functioning despite terror and injuries. In one mission over Wilhelmshaven, an 88mm shell detonated 3 feet from the aircraft's nose, blowing away the entire plexiglass bombardier compartment and severely wounding the bombardier. Yet the aircraft maintained structural integrity, and Morgan successfully flew it back to England for an emergency landing. The psychological resilience required of B-17 crews derives partly from confidence in their aircraft's ability to bring them home despite battle damage. Sergeant Anthony Romano, having completed 15 missions as a ball turret gunner, describes the mentality. You know you're flying into hell every mission, that German gunners are going to hit you, that fighters will attack, that some aircraft won't make it home. But you also know the B-17 can take incredible punishment and keep flying. You've seen bombers return with damage that looks impossible to survive. That knowledge doesn't eliminate fear, but it gives you something to hold on to when flak is exploding around you and you hear fragments hitting your aircraft. The maintenance burden of repairing heavily damaged B-17s strains ground crew capabilities as bombers return from missions requiring hundreds or thousands of man-hours of structural repair, engine replacement, and systems restoration. Technical Sergeant Anderson's team works around the clock to return Captain Fisher's aircraft to flight-worthy condition, a process requiring 3 weeks and approximately 2,400 man-hours of labor. The damaged wing requires complete structural rebuild with new spars fabricated and installed. The destroyed engine must be replaced entirely. Fragment holes throughout the fuselage must be patched with aluminum sheet, and all control cables must be inspected and replaced if damaged. The economic calculation proves favorable. The cost and labor to repair extensively damaged aircraft remains less than the cost of replacing them with new production, and repaired aircraft return with experienced crews whose survival value exceeds that of new crews in new aircraft. German fighter pilots, initially confident they could destroy American bomber formations through aggressive attacks, gradually recognized that B-17s prove remarkably difficult to bring down even when hit repeatedly. Oberlieutenant Franz Stigler, an experienced Me-109 pilot with 28 victories, describes the frustration. You make a perfect attack, see your cannon shells striking the bomber, watch pieces flying off, then the aircraft maintains formation and continues flying. American bombers seem to absorb damage that would destroy 3 or 4 of our fighters. You must hit them repeatedly in critical areas, cockpit, engines, wing roots, to ensure kills. Body hits that would doom a fighter often prove insufficient against flying fortresses. The statistical analysis of B-17 combat losses versus missions flown reveals patterns that guide tactical evolution and inform crew training. Aircraft lost to fighter attacks concentrate damage in cockpit areas, engine nacelles, and wing roots, where structural failure or fire becomes likely. Losses to flak show more random distribution, reflecting the essentially statistical nature of anti-aircraft fire, where hits depend more on mathematical probability than targeting precision. The data suggests that increased defensive firepower deters fighter attacks more effectively than additional armor, leading to the B-17G's chin turret modification that addresses the frontal attack vulnerability German pilots increasingly exploit. The development of formation tactics specifically designed to maximize B-17 survivability represents the integration of aircraft capabilities with operational doctrine. The combat box formation, with aircraft arranged in staggered altitude and lateral spacing, creates overlapping fields of fire from defensive guns while maintaining tight enough proximity that damaged aircraft can remain within formation protection. Lead bombardier techniques, where only the lead aircraft in each box aims precisely, while others drop on the leader's signal, reduce individual aircraft exposure during the vulnerable bomb run when straight and level flight becomes mandatory. These tactics, refined through costly trial and error, transform B-17 capabilities from theoretical design specifications into practical operational advantages.
Captain James Hansen, intelligence officer analyzing crew debriefings from the Schweinfurt mission, notes recurring themes in accounts from severely damaged aircraft. Crews initially believe their aircraft is doomed when hit hard, experience shock at discovering the bomber remains controllable, then develop fierce determination to bring the aircraft home. The psychological transition from expecting death to recognizing survival possibility proves critical to mission completion, as pilots who believe their aircraft can survive fight to maintain control rather than ordering abandonment of potentially salvageable bombers. The B-17's reputation for toughness creates positive feedback, where crews push damaged aircraft harder because they believe survival remains possible. The technical investigation into why some B-17s survive catastrophic damage while others don't reveals complex interactions between damage location, aircraft loading, crew actions, and pure chance. Aircraft hit in bomb bays while carrying armed ordnance typically explode with total loss of crew. Aircraft suffering oxygen system damage at high altitude force crews to descend into altitudes where German fighters operate more effectively. Hydraulic system damage complicates landing even if aircraft reaches friendly territory. Control cable damage can render aircraft uncontrollable despite intact structure. The survivability equation involves dozens of variables, any of which can prove decisive, but Boeing's design philosophy of redundancy and damage tolerance shifts probability toward survival more often than competing designs. German efforts to develop weapons specifically optimized for destroying B-17s include experimentation with larger caliber aircraft cannons, air-to-air rockets, and even aerial bombing where fighters drop small bombs into bomber formations. The Mk-108 30mm cannon, entering service in late 1943, delivers sufficient destructive power that 3 to 5 hits typically destroy a B-17, compared to the 20 or 30 hits often required with 20mm weapons. However, the Mk-108's slow muzzle velocity and limited range forced German pilots to close within defensive gun range, exposing them to return fire from bomber gunners. The tactical trade-off, more destructive weapons requiring more dangerous attacks, reflects the broader challenge of defeating aircraft specifically designed to survive in defended airspace. The training program for replacement B-17 crews incorporates lessons from combat veterans, emphasizing damage control procedures, emergency operations with failed systems, and the psychological preparation for continuing missions despite battle damage and casualties. Student pilots practice flying with simulated engine failures, operate with degraded control systems, and learn emergency landing procedures for various failure modes. The training acknowledges that crews will experience damage and casualties, preparing them mentally and technically to continue functioning despite circumstances that might paralyze untrained personnel. The publicity surrounding the B-17's combat record, while serving important morale and propaganda purposes, sometimes obscures the harsh reality that 60 crews didn't return from Schweinfurt, and hundreds more experienced terrifying close calls with death. The famous photograph of Memphis Belle returning from its 25th mission, taken as the bomber lands at Bassingbourn,
shows an aircraft that appears intact and undamaged, reinforcing the invincible fortress image. Less publicized photographs show bombers landing with gaping holes, destroyed engines, and blood-stained interiors, images deemed too graphic for public release, but which tell more complete stories of what strategic bombing actually involves. Major Whitfield's comprehensive damage analysis, completed in December 1943, quantifies B-17 survivability through statistical measures. 73% of B-17s sustaining major battle damage, defined as damage requiring more than 200 man-hours to repair, returned to base, compared to estimated 45 to 50% for other heavy bomber types based on British experience with Stirlings and Halifaxes. The improved survival rate translates directly into preserved crew experience and reduced replacement training burden, strategic advantages that accumulate across thousands of missions. Whitfield's report recommends no major design changes to the B-17, concluding that the existing design achieves optimal balance between survivability, payload, and operational performance. German post-war technical assessments of American strategic bombing equipment consistently identify the B-17 as the most professionally engineered bomber of World War II, though German analysts note that the Luftwaffe's strategic situation made effective countermeasures impossible regardless of American aircraft quality. General-Major Adolf Galland, commander of German fighter forces, states in 1945 interrogations, "The Flying Fortress lived up to its name. Our pilots found it extremely difficult to destroy even when achieving multiple hits. The combination of structural strength, defensive armament, and formation tactics made American daylight bombing possible despite our fighter and flak defenses. A lesser aircraft would have suffered prohibitive losses that forced abandonment of the daylight bombing campaign." The economic analysis of B-17 production and operation reveals industrial capacity advantages that prove as important as engineering excellence. Boeing, Douglas, and Lockheed Vega produced 12,731 B-17s between 1941 and 1945. Averaging over 270 aircraft monthly during peak production. The production rate allows rapid replacement of combat losses while building force strength, creating numerical superiority that overwhelms German defenses regardless of individual aircraft quality. German industry producing fewer than 1,900 heavy bombers, HE-177, over the same period, cannot achieve similar force levels even before considering that B-17 survivability means more aircraft remain operational longer. The human cost of the strategic bombing campaign, even with the B-17's exceptional survivability, proves staggering, as the 8th Air Force suffers over 26,000 fatalities and 28,000 additional casualties among aircrews. The 20% casualty rate among bomber crews exceeds that of any other American military branch, reflecting the mathematical inevitability that even aircraft designed for survivability eventually sustain fatal damage when subjected to repeated combat exposure. The psychological toll on crews completing 25 mission tours approaches that of sustained ground combat, with many airmen exhibiting symptoms of combat stress disorders that 1940s military psychiatry inadequately understands or treats.
Captain Fisher, having recovered from his wounds and returned to operations, flies an additional 12 missions before completing his combat tour in March 1944. His experience surviving the October 14th direct hit shapes his approach to subsequent missions as he develops almost superstitious confidence in the B-17's ability to bring him home. In post-war interviews, Fisher acknowledges this belief probably constituted denial of genuine dangers, but argues the psychological benefit of believing in his aircraft's invincibility proved operationally valuable. "If I'd thought every flak burst might kill me, I'd have been paralyzed with fear.
Believing the B-17 could survive anything let me function despite terror that would otherwise have been overwhelming. The technical legacy of B-17 engineering influences post-war aircraft design across military and civilian aviation as Boeing's emphasis on structural redundancy, damage tolerance, and systems reliability becomes industry standard practice. The concept of fail-safe design, where single-component failures don't compromise entire systems, derives directly from B-17 experience with battle damage. Modern transport aircraft incorporate self-sealing fuel tanks, redundant control systems, and compartmentalized structures owing intellectual debt to lessons Boeing learned building bombers that could absorb punishment and continue flying. The B-17 crews who survived the war carry lifelong appreciation for the aircraft that brought them home, despite damage that should have killed them. Veterans organizations like the 91st Bomb Group Association maintain the B-17's legacy through reunions, memorials, and historical preservation efforts that ensure younger generations understand the combination of engineering excellence and human courage that characterized the strategic bombing campaign. The surviving flyable B-17s, maintained by museums and enthusiast organizations, serve as tangible connections to the era when American industry and engineering met warfare's harshest test and proved equal to the challenge. Hauptmann Vogel, surviving the war and the subsequent Soviet occupation of his region, eventually emigrates to West Germany where he works as a civil engineer. In 1978 correspondence with American veterans organizing a Schweinfurt mission reunion, Vogel writes, "I watched your bomber take that direct hit and continue flying. I knew in that moment that we could not win, that American engineering and industrial capacity exceeded ours by margins we could not overcome. The Flying Fortress earned its name that day over Schweinfurt, and every day your bombers returned despite our best efforts to destroy them." The final accounting of B-17 combat operations documents 291,508 sorties flown against European targets, 640,036 tons of bombs dropped, and 4,754 aircraft lost to all causes. A loss rate of 1.63% per sortie that, while seemingly small, translates to roughly 25% probability that any individual bomber would be destroyed during a 25-mission tour. The statistics capture the essential tension of strategic bombing. Individual mission survival rates high enough that crews could reasonably hope to complete tours, but cumulative probabilities ensuring substantial casualties over extended campaigns. The B-17's exceptional survivability, keeping loss rates at sustainable levels despite intensive German defenses, made the difference between a strategic bombing campaign that achieved its objectives and one that collapsed under unsustainable losses. The story of the B-17 Flying Fortress ultimately transcends technical specifications and combat statistics to become a testament to engineering philosophy that prioritizes crew survival and mission completion over performance optimization. Boeing's design team, lacking combat experience when they created the aircraft in 1935, nonetheless intuited that survivability would prove more valuable than speed, altitude, or payload. That intuition, validated through 4 years of the most intensive aerial combat in history, created an aircraft that could absorb direct hits from 88mm flak shells, continue flying with catastrophic structural damage, bring wounded crews home across hundreds of miles of hostile territory, and do this repeatedly across thousands of missions. The bomber that Hauptmann Vogel watched survive his battery's direct hit on October 14, 1943, represented more than American technological achievement. It embodied a design philosophy that valued human life highly enough to trade performance for survivability, that built redundancy deep enough to function despite massive damage, and that trusted engineering excellence to overcome the seemingly inevitable mathematics of aerial warfare that said bombing Germany in daylight should be impossible. The Flying Fortress proved it possible, one damaged bomber limping home at a time.